In previous videos, we've talked about finding the maximum and minimum value of a quadratic form. And in this video, we're basically talking about the same thing, but we're giving it a fancy new name, which is constrained optimization. Now, the constrained there means our values of our x vector, the magnitude of that vector, must be 1. That's the constraint. And the optimization part is that we're trying to either maximize or minimize the value of our x transpose ax. So that's the fancy name for it. And the reason we're covering this in more depth is that we've sort of discussed how you can use change of variable and how you can use eigenvalues to solve this problem, but there's a simpler way of doing it involving the same methods. So we have our matrix A, and we find its eigenvalues, then we find its eigenvectors, and we normalize them. If we order those eigenvalues such that the largest eigenvalue is lambda 1 and the smallest is lambda n being the size of whatever matrix we're working with, and we identify the corresponding eigenvectors, the largest eigenvalue will be the largest value of the quadratic form, and the smallest eigenvalue will be the smallest value of the quadratic form. And the associated eigenvector, normalized of course, will be the coordinates, kind of the not the coordinates because it's vectors, but they will be the x vector that gets us to that optimized point. We've obviously normalized because they have to be within this constraint. Now, there's a problem here though, because if we want to conduct constrained optimization, and we find a matrix with repeated eigenvalues, say 1, 1, minus 1, and we don't find corresponding orthogonal eigenvectors to that, well, what happens? So this is where we come into Gram-Schmidt again. We can identify, sometimes by observation, but sometimes we have to use things like Gram-Schmidt, what the additional eigenvector is, and we can normalize it. So all we're doing here is, we find our u1 and our u2. We go, hang on, there's a third eigenvector here. And so we just use Gram-Schmidt to find that third eigenvector for that final corresponding eigenvalue. And we can again solve this problem when we have the x vector we need, normalized of course, and we have the eigenvalue we need. So that's constrained optimization. It's really something we already talked about in the video about maximizing and minimizing the value of quadratic forms. I mean, that is constrained optimization. But it's important to know how to do this with repeated eigenvalues. And it's important to know that you can use this here. You can just order your eigenvalues and order your corresponding eigenvectors, and you have solved the problem. And there's a proof for this, but because these videos are for my own revision, I often don't bother with proofs. Because can you imagine me writing a proof in Microsoft Paint with this handwriting? All right, thank you for listening.